So John Nash suggested that we do an optimization problem from Calculus 1 to determine the Nash arbitration point. So let's walk through that example. So he said, look, suppose that we have some status quo point. I'll talk a little bit more about that in just a second, but suppose we could establish the status quo point of the game. Then what we'd like to do is we'd like to draw a rectangle that has its bottom left corner at the status quo point and has its top right corner at this Nash arbitration point N. And then the rectangle will have sides that are parallel to either the X or the Y axis. So here's what that'll look like. We are just taking a look at the maximum area of this rectangle where the point N moves along the northeast boundary, but not the entire boundary, just the Pareto optimal portion. Now, a word about the security levels, the status quo point. There are a couple of options that we could have. The security levels are one popular option. You might think the Nash equilibrium would make sense. That's not how Nash decided. Nash had an idea, which you've seen on the title slide, talking about an optimal threat strategy. We'll talk about that in a minute. At the moment, I just chose an arbitrary status quo point that doesn't have much to do with the game, but does make the geometry and calculus problem solving easier to understand. So that's what I'm going to use for my explanation. So let's do this optimization. Remember, every optimization problem starts off with something we're trying to maximize or minimize, and we want to maximize this area. The area of the rectangle is just the difference in the x-coordinate of the Nash point minus the x-coordinate of the status quo, which was 1, and y minus the y-coordinate of the status quo, which was 2. So this is the area of our rectangle. The problem being it has two unknowns. So like all optimization problems, there are some constraints, and we're going to be able to use those constraints to eliminate a variable, and then we'll be able to do typical calculus 1 differentiation. So we know that this Nash point has to lie on either line segment BC or CD. That's the Pareto optimal boundary. But it also has to lie to the right of Rose's security level and above Colin's security level. So we're going to use that constraint and make sure that when we solve this optimization problem, we find solutions that are in the appropriate intervals. So one quick note, the B, C, and D, they're not related to strategies. They're just an easy way to reference these points, these vertices of the payoff polygon. So please don't get confused. So if the Nash point is on segment BC, we need to determine the line that contains that segment so we can use it as a constraint. So we're calculating the slope, which is -1/2. And then we just use the point slope version of a line. And I chose to use this as my point. And of course, the 1/2 is the slope. And you can see the calculations. Y minus y naught equals -1/2 times x minus x naught. And when you simplify that, we get our first constraint. So we know that the line segment BC is contained in the line y equals -1/2 x plus 22. So we're going to substitute for y in our area equation. And then we'll be able to do calculus. So here we go. We've substituted in equation 3 right here. Now we have a single variable function in terms of x. We just subtracted the 2 here. Now I'm going to expand this binomial. You could take the derivative with the product rule right here if you'd like to. I preferred to expand and simplify, and I'm going to take the first derivative and set it equal to 0. Right, it's not equal to 0, it's a function, but we're trying to find the critical points which happen when we set this equal to 0, and when I do, you'll see that x equals 20.5. But notice what's going on with this solution, right? 20.5 is way over here. I don't even know if you can see that on the side of the screen, and it's not within the interval, right? We were looking for, in calculus, we were looking for a maximum in this closed interval between the x-coordinates of B and C. And we didn't find that. And of course, with our Nash arbitration, we would have also had to make sure that it was larger than this 5.6. So we were looking in here, we didn't find it. The x-coordinate is way out here. So what we know is that the maximum has to occur at one of the endpoints. Well, B is not in the negotiation set, so the solution is going to be at the point C, and we'll calculate that area at C and find that the area is 112 square units. So that's the maximum for the first constraint. Now we're going to use a second constraint. Now we're going to write the equation of the line that contains the segment CD. So now we have this line. And again, we're going to look and see if there's a maximum in here for this downward facing parabola, or if the maximum occurs at one of the endpoints. So you should double check that this is what you get when you write the equation of the line through those 2 points. Substitute into the area equation. Again, I'm going to simplify and expand before I take the derivative. Here we go. Now I can take A prime. I can set that equal to 0, and when I solve it, I find that the x value is 6.1. Unfortunately, while it's near and on the negotiation set, right, this 6.1 is about here, it's on the wrong line segment. We were trying to optimize along the line segment CD. So once again, the peak of the parabola is outside the line segment, so we have to check for the values at the endpoint. Well, we already know the area of C, the C that was calculated earlier. And so we calculate the area at this point D, but it's only 54, which is smaller than the 112. So now we know that the absolute maximum on the negotiation set for that point N is when it's located right at the vertex C. So that happens sometimes. I have a further example I'm going to show you where we can move this point D, and we'll see how that changes what's happening with the solution. But for right now, we just got one of the endpoints. And B wasn't in the negotiation set, so we'd even bother calculating it. Here's the results. This is the maximum area obtained, and it happens when x is equal to 8. So this is the Nash arbitration point. So that concludes the calculus part. I'm going to go through this with more geometry in the next portion of the video.